Welcome to the second semester of organic chemistry. My name is Dr. Pike, and we start off this semester on chapter 12 talking about radical reactions. Now, before we begin talking about radicals, I want to have a very brief review over what type of reactions we've already looked at in the first semester. So the first semester really concentrated on four main types of reactions: SN1, SN2, E1, and E2. So we call them substitution and elimination reactions. And there are some very characteristic properties of these reactions in that they all involve electrophiles, which are cations, and nucleophiles, which are anions. And so because of this ionic nature of these types of reactions, they are polar in nature. And of course, the solvents were also polar in nature as well. If you recall, we dealt with polar solvents with substitution reactions, such as water, ethanol mixtures, acetone, DMF, DMSO, acetonitrile, and such. Radicals, on the other hand, are very different species. They're neutral and they're nonpolar. And so there's a little bit difference in terms of the way that they behave. One of those differences is the actual mechanism of radicals. So radicals involve chain reactions, which are very different from substitution and elimination reactions, and we'll get into that throughout this chapter. Now, they also involve using only one electron, so the movement of one electron versus the movement of two electrons. And if you recall, in the first semester, we talked about heterolytic cleavage, which uses the double barbed arrow in terms of mechanisms. So in this chapter, we're going to focus on a homolytic cleavage, which uses fishhook arrows. So we have basically lines that have one hook at the end of them to denote the movement of one electron. So to preview, for this chapter, you need to be able to draw resonance structures of radicals. Now, I know you're fairly comfortable, or you should be fairly comfortable, with drawing resonance structures of carbocations and carbanions. Drawing resonance structures of radicals is a little bit different because we're using only the movement of one electron. So for example, here we have what is called an allylic radical. And so you see that there is a double bond, and on the allylic carbon, so an allylic carbon is a carbon adjacent to a double bond. So on that allylic carbon, you see that one dot, which denotes one electron. Now, we can draw resonance structures by moving that one electron in between, to form a bond in between that allylic carbon and the vinylic carbon. And so we're placing that bond to form another bond, and we need one more electron, and so we get that electron from the pi electrons of that double bond. So we're going to take one electron of those two pi electrons, and we're going to now form a new double bond. And that leaves us with one electron left over, and so that one electron that's left over goes to the other carbon. The result is this resonance structure. And so again, we form another allylic radical, and these two structures are in resonance with one another. Now that resonance is going to help to stabilize things, which we're going to see becomes important later on. Now we can do something very similar with what's called the benzylic radical. So this is where you have a benzene ring, and you have a carbon coming off of that benzene ring. That carbon is called a benzylic carbon. And you see that one dot above that carbon. So that, again, that dot represents a radical. And again, we have a situation where the carbon adjacent to that radical is an sp2 carbon. And so it has pi electrons that we can use one of those pi electrons to create a new double bond with the radical. So we take that radical, we donate it in to form a double bond with one electron from that pi bond, and the other electron goes to the adjacent carbon. And so the resonance structure looks like this. Now you can see we've disturbed aromaticity, which we're going to get into in later chapters. And so this radical isn't quite as stable as the previous radical, but it is a resonance structure. And not only is it a resonance structure, but you can see that it is also an allylic radical. And you can also see that on both carbons adjacent to it, we have double bonds. And so I can take a look at the double bond to the left of it, and I can create another resonance structure from that. And I end up with the second resonance structure, which is shown right here. Now, as you can possibly imagine, again, this scenario leads us to a situation where I have two adjacent carbons. Both of them are sp2 hybridized, and so I can take a pair of electrons from the top of the ring and I can draw another resonance structure. And it looks like this. And so these are 4 resonance structures of the benzoylic radical. Now each one of these resonance structures is not the same in energy. The one on the left is the most energetically favorable, but because of the delocalization of that radical electron, we see that the benzoylic radical can be stabilized in this way. Again, this is going to become very important later on.